Imagine a silent, invisible threat lurking at the very edge of our power grids, a vulnerability so overlooked, it could jeopardize the stability of our entire energy infrastructure. This is the hidden risk of utility operating systems at the grid edge, and it's far more critical than most realize. As utilities increasingly lean on edge computing to modernize aging systems and enhance efficiency, from automated grid balancing to remote fault detection, they are inadvertently exposing themselves to a new breed of cybersecurity challenges. But here's where it gets controversial. While the industry focuses on network segmentation and threat detection, one foundational layer remains dangerously neglected: the operating system, OS. Andrew Reinhardt, Chief Technology Officer at Sidro Labs, highlights how the expanding edge footprint is reshaping the security landscape. Edge nodes, deployed in transformer stations, distributed energy resources, and alongside smart meters, often operate in remote, unmonitored locations. These systems rely on intermittent connections and may go years without maintenance, making them prime targets for adversaries seeking to disrupt critical infrastructure. Yet, the security conversation rarely dives into the OS-level risks that underpin these systems. And this is the part most people miss. Traditional Linux distributions, designed for servers or desktops, still power many operational technology, OT, systems, grid controllers, and IoT gateways. While these OSes are familiar and flexible, they weren't built for today's threat environment or the unique demands of edge deployments. Their mutable nature, allowing configurations to drift, file systems to be altered, and security settings to change over time, turns them into liabilities in the edge's unpredictable conditions. A system secure on day 1 can become vulnerable by day 1000, and you might never know why. For utilities managing thousands of edge nodes, a small misconfiguration can become a systemic weakness. Attackers don't need sophisticated zero-day exploits when they can target outdated packages, exposed services, or poorly secured update mechanisms. Here's the bold truth: without addressing OS-level risks, utilities are building their edge infrastructure on shaky ground. So, what's the solution? Enter the concept of immutable operating systems. Unlike traditional OSes, immutable systems cannot be altered during runtime. They boot into a predefined, verified state and remain unchanged, eliminating the risk of tampering or misconfiguration. This approach is a game-changer for utilities, where edge systems are often inaccessible and physical intervention is costly. Immutable systems reduce human error, simplify audits, and ensure every node operates with the same cryptographically verified configuration. Updates become safer too. Instead of patching live systems, utilities can replace the running image with a new, verified version, ensuring atomic updates that either succeed completely or fail without compromising the system. This rollback safety is crucial in environments where uptime is non-negotiable. But here's the controversial question: are utilities willing to rethink their approach to edge security? Some energy providers are already leading the charge, deploying thousands of immutable edge nodes to balance national grids and support distributed energy resources. Early results show increased operational flexibility, reduced overhead, and a new baseline for secure by design infrastructure. Yet, many remain hesitant to abandon familiar, but flawed, systems. As the edge becomes integral to utility operations, the industry must prioritize minimal, declarative, and tamper-resistant systems. Operating systems should include only essential components, eliminate unnecessary attack surfaces, and enforce behavior through code. Security should be verified cryptographically, not assumed, and updates must be safe and reversible. Is this the future of edge security, or are we overlooking a better approach? Weigh in below. Let's spark a debate that could redefine how we protect our energy infrastructure.